gonna do now, right? I said here, this is on DRCPT. Diameter, radiuses, cyclic quads, parallel lines, tangents. So we don't have much to look at really here, because when you're looking for a diameter, you're gonna go to the center, obviously. Once you go to the center, because the diameter has to be a line passing through the center. Once you go to the center, you automatically identify two lines that are the radius of the circle, yes, so they are equal. That's why, fortunately, you put 5 and 5. Furthermore, you have two other lines coming from the center. They are not equal, but they make up part of our theorem, theorem 1. So that makes life easy for us. So it says here AB is 8. So automatically, since AB is 8, as you wrote down here, this is 4, this is 4, because they are equal to each other because of theorem 1, which we need to tell them we know once you use it. And then it says OF is 3. Okay, fine. OE is 4. AF is equal to FB. Okay, they told us, they didn't have to. We need to know that for ourselves, but they told us, just being generous. And then it says here OE is perpendicular to CD. Here they didn't tell us, but we can already put that for ourselves. And then when we need it, we can give them the reason why we know those are equal. So they say here, calculate the length of chord CD. So the idea is, since if you're looking at where CD is the part of the sketch that has the least information. So the last thing you want is to bother yourself with CD when you do not yet have information around here. But I see here you wrote that F1 is equal to 90. Okay. Line from center to midpoint. Yes. Okay, that's fine. And then you wrote here OF squared is equal to, OA squared is equal to OF plus AF. That's Pythagoras. Yeah, because the idea is, you see, this side is the one that's like open. So you want to take information from the side that is populated to the side that is not. So here you had the 3 and the 4. So fortunately, because you know that these two are equal, the 90-degree angle is what was not given. You see, so you stating that this is 90, obviously this is essential, so that you can eventually use Pythagoras. So you mentioned that it's 90 degrees, and then you use Pythagoras, then you got the 5 here. Perfect. You see, because once you have the 5, then you could say that OP is also equal to 5, or rather, I think you wanted to say OD. OD here is also equal to 5. The moment OD is also equal to 5, you can easily then work out ED and then double it afterwards. You see, ED here squared. No, that's not the hypotenuse. The hypotenuse is OD. So let's say here OD squared is equal to OE squared plus ED squared. You see, so OD here is 5. OE is 4. ED is ED. We're trying to isolate it. So this is going to be like 25 minus 16. And then we're going to get, what is this? 25 minus 16 is what? 9. ED squared. So square root this, square root this. This is going to give you a 3. There is ED. There you go.
Okay.
So now, since now you know that ED is a 3, you can then tell them that you know that ED is the same as EC. You can say here ED is equal to EC, right? And the reason is as this one, line from center to midpoint. Line from center.
Can I also write perpendicular from center to chord? Because that's a chord as well.
Yeah, so here you can say line from center bisects chord.
Oh, okay.
Bisect chord. This one is actually the way you can always refer to theorem 1. Line from center bisects chord. You know, line from center bisects chord
Okay.
is what you're seeing. And then here, having to have mentioned that this is 90 degrees.
Mhm.
Same idea. Line from center bisects chord is the way you refer to the theorem. It's 100% okay for you to say it like that. So, is that okay?
Mhm.
Okay. Anyway, so for this what? This is here's the past paper. We're gonna look for the what you may call the Euclidean geometry section. And then we're gonna go through wait, there's no Euclidean geometry here. Oh, this was 2011. Oops, gotta go back. Pick something from 2014 maybe. Yeah, no, 2012, sorry. That's when they started including Euclidean geometry in the syllabus. So let us look for it. So we're just gonna look for Euclidean geometry question, right? Probably somewhere down here. Run. Oh. No ways. Okay, let me go to 2013, 2014 then. 2014, 15. Euclidean geometry. So we just need to pick out like one slightly congested sketch so that we can see the train of thought that we need to follow when we work with Euclidean geometry questions. This one seems like a good question. But then, yeah, these all seem like good questions. Yeah, they do all seem like good questions. They really do. Let me see. But I think let's go through this one. This one seems like something that they like to ask, or something that they can potentially ask. So let's look at this one, because the way we're going to be talking about this question, firstly, we're definitely going to use Dr. Cape Town, and the idea is we're just going to take it slow, because these kinds of questions, they look difficult just because of the way the circles may be aligned or whatever. Like here, this is like multiple circles. So it's normal for that question to look unappealing, but it is fine. You should still just be able to deal with it without any issues. So firstly, we said Dr. Cape Town. Dr. Cape Town saves lives. So it's just a matter of writing out the acronym, because once the acronym is written, it's almost like opening a small compartment in your brain to start thinking when you write out the acronym. So when you see here, we're saying that we have a question, you automatically immediately write DRCPT before you start. And then let's see what we're dealing with. Diameter. Wait, no, before we do any of that, let's read the question. It says, in the diagram, PQ is a common chord, okay? PQ is a common chord of two circles, fine. It almost looks like the diameter of the small one, but we don't know until we have the facts. Then it says, the center M of the largest circle. So M is the center of the largest circle. That's very important. That's a lot of information all in one statement, because look, the moment you see that M is the center, you see that there are two lines that are the radius of the circle.
Yeah.
Yeah. Hence why we say the moment you are thinking of Dr. Capron and you're reading a statement, these two should be in mind because now you have the center. So you should be looking for a diameter. This does not have a diameter, the big one. They've not given it to us. But then it has a radius there and a radius there. So that now in our sketch, if this is X, already we know that this is going to be X. And we need to know that kind of information because it helps us.
Yeah.
You see. Yeah. Secondly, they said PM and Q is a cyclic quad. So let's see where that is. P, M, and Q is a cyclic quad. The moment they mention cyclic quad, look for the three laws. You may not find all of them, but there has to be at least one. You see, the fact that this is a cyclic quad, already you know that you have angles that are exterior angles of your shape. And the exterior angles of your shape will be equal to the opposite interior angles. So already what we know here is that this angle here, this is an exterior angle. It's equal to that one. You see it? Yeah. The reason why I'm pinpointing this one is because this one is equal to X. So if this one is equal to X, this one will be equal to X automatically also. You see? Yeah. So that kind of information, don't take it for granted. Because when you start using it, all you will need is your reasons. Because your questions for Euclidean geometry are mainly answered during the process of you reading your description. Because once you're done with the description, it's just like marks. So, secondly, you would want to look for lines that are like crisscrossing each other in your cyclic quad. We don't have that. So since we don't have that, we don't have this law. We only have found this so far. We can also spot it maybe here. This is an exterior angle, and this is the opposite interior one. But the thing is, normally if you see that the opposite interior one is like cut, you know, and it's like two angles put together, usually that may not be very useful, but sometimes it can. But in this situation, we can just take note of it, but not give it too much attention. Then they say it here, Qn is produced to R. So Qn goes all the way to R. That's important. The other thing we missed in the beginning, which was very crucial, is that this is the angle in the center. Remember we said the moment you're seeing angles in the center, you should think of laws that deal with angles in the center, just like this law.
Yeah.
You see. So this one here, if this is X, this becomes 2X. So here we should have spotted it because this angle in the middle here is double this one here. You see, we don't want to take that for granted. But you see, the one thing that helped us remember was when they mentioned R. Because anything they mentioned, look at it nicely. They spoke about Qn going to R. Then the next question would have been, but where is R going on? It's an angle. So there's an angle, it goes to P. The line also goes to Q. So which other angle goes to P and Q? The one in the middle. So we now know that this is double that one. And that's definitely going to be useful. You see. Secondly, they said here a point, they said Qn is produced to R, and then said a point on the largest circle. Mn, where is Mn? Mn produced meets the chord. Mn produced meets the chord PR at S. That's very important. It's also another thing we missed. Do you see that MS is a line from the center of a circle?
And
yeah,
yeah,
a line from the center of a circle, what does it do to a chord?
it bisects the chord.
It bisects the chord. And what else happens at the point of intersection?
It means that, let me see.
It's cutting it here, and then what?
Then 90 degrees. So it's a
Yes.
right angle.
Exactly. Exactly. So do you see that from reading the statement, there's so much information that they did not put on the image, but
Yeah.
from reading the statement, we have all of it. And it looks like everything came from these three. From diameter, we don't have, but we focused on the center. Radius we have, and it's all coming from the center. Cyclic quad's fine. But then everything about this center, you see, when we deal with Dr. Kaplan, the moment we spot a center, we should go through these three. You see, theorem, this has a center there. This also has a center. This also has a center. This also has a center. So that we're able to properly populate our question with like essential information. You see, now that we have gotten all this information, you're gonna see that the questions that we have to deal with, they're almost gonna seem simple because it's just going to be reasons for all these things that we have already just spotted. Are we on the same page? Okay, let's dive into the questions. So diving into the questions, we should not even expect anything surprising. For example, the first question, they're asking, why is N2 equal to X? Why is N2 also equal to X? What's the reason?
Let me see. N2.
Because remember that they told us this is a cyclic quad.
Oh. It's a circle then. N2 is equal to X. Let me see. I think I know, but I'm not sure.
Like, what do we know about that cyclic quad? What is one of the laws of cyclic quad?
Okay, let me see. If N2 is equals to X.
Yeah, because N2 is equal to this. Because remember, the only X that they gave us is this one, the one here. So why is that one equal to that one?
First, to figure out the triangle.
Which of these laws?
Oh. Okay. Now I see it. So the one.
You're saying they didn't ask for the size. They're asking why is N2 equal to
why
X?
is it equals
like
to X?
Yeah. Like,
Okay,
why are
let
these
me see how do you put it in words? I can't put it in words.
Yeah, because the thing is, this one is it's just a theorem. The theorem is that N2 is an exterior angle of a cyclic quad. You see? Exterior angle of cyclic quad. That's all you say. Because remember, P, Q, N, M is a cyclic quad. So as long as this is the cyclic quad, the angle outside is equal to that one. Have you guys touched on this law yet? Not yet.
Two theorem 3, looking at this paper.
Okay, now I get you. I understand. Okay, so this one we can leave it out for now. It's fine. But anyways, the reason why N2 is equal to X is because this is an exterior angle of a cyclic quad. A cyclic quad is a four-sided shape where the 4 points are touching the circle. So 10.2.2 says, write down another angle equal in size to X. So which are the angles? Which other angle did we say is equal to X?
Q1.
Q1. And what's the reason?
radii,
Yeah, we have to tell them
because
that
M is
these
the
are
center.
equal. Yeah, so for 2 marks, so firstly we have to say that Q1 is equal to X. Then now we can say the reason is base angles of an so how do you spell isosceles triangle? There we go. That's fine, right?
Base
So now
angles
they're
of
asking
an
us,
isosceles triangle.
pardon?
I'm saying base angles of an isosceles triangle.
Yeah, so the next question now, determine the size of R in terms of X. What can we do? Because remember we said this is double that. They say we should
size
get
of
R in terms of X.
So R is x2 because angles at the center is 2 times the angle at the
Well,
circumference.
well, remember, I think you know what you want to say, but then you're just rushing it. Firstly, what is the angle M1? What would you do to get M1?
M1.
Yeah, in terms of X. Because if X and X were numbers, what would you have done to get M1?
Minus x minus the 2x's from 180.
Yes. So M1 in terms of X is just 180 minus 2x. The thing is, right, when you see them saying that you should get an angle in terms of a variable, what they mean is they just mean that imagine the variable was a number. And then they are saying if the variable was a number, what would you then have done to work out the question that they're asking if the variable was a number? So for example, if you're asked to get M1 in terms of X, they're just us saying that look at X as a number and then tell us what you would do to get this angle. You would say 180 minus this 1x minus the other x, which is 180 minus 2x. So now, since we're talking about R, they said get R in terms of x. You cannot get R without getting this, which is why you were thinking of saying 2x, because what you were trying to say is that we should just double this one to get this one, which is all we need to do. So 180 minus 2x, we're just going to double it, you see. So remember, mentioning this here, we're going to say M1. Remember, we have to write statement and a reason for what we did. M1 is equal to this. And then we give them a reason. The reason is, what is the reason for saying this is 180 minus 2x?
Angles equals opposite sides or interior angles of a triangle.
Interior angles of a triangle. That's the one we should use. Interior angles of a
triangle.
That's how we said M1 is what it is. So that now that we have M1, we can say that M1, we can say here R is double M1. What's the reason for writing this?
Angle at the center is equals to angles at the center is 2 times the angle at the circumference.
Yes, angle at center equals double angle at circumference. That's the reason, you see. So here you can now conclude and say, therefore, R is 2 times 180 minus 2x. You see, the brackets are important so that you can multiply inside and you can say 360 minus 4x. You see, that's your value of R in terms of x. They'll give you 3 marks. The last one says, prove that PS is equal to SR. You see, PS, we should prove that it is equal to SR. You see, they're asking us to prove something that is directly in our face because it's just a theorem. that we need to invoke. You see?
Mm-hmm.
Yeah. So we just have to tell them the information we know, because remember the sketch did not have this, the sketch did not have this. So as we put it on our sketch, we tell them the reason. So the first thing is we're gonna tell them that this is a 90-degree angle. And what is the reason for us telling them that this is a 90-degree angle? Wait, hold on. We cannot say that because, oh, wait, hold on. We cannot, what you may call, we cannot, what's the word? We cannot assume, wait, no, line from center. The thing is, one of two things have to be given. The lines have to be perpendicular, or the lines have to be equal for us to be able to state the other. But then hold on, because not all lines from the center bisect the chord, only the ones that meet at an angle of 90 degrees. So what we'd have written down there was more like an assumption actually, because none of the two ends of the information is given. There's no 90-degree angle, and these are also not equal. No, these are equal because it's the radius of a circle. Yeah. Yeah. No. This is not the center. The center is M. Yeah. So you can see Euclidean geometry sometimes can play games.
So if it's from center to chord, because that's what all my things say.
Yeah, true. The only thing is they have not told us that this is 90, and they've also not told us that these are equal. So we cannot assume that because it just looks like this. This is a 90-degree angle. If it was given like this, we would then be able to say these are equal because of the law. But the thing is, the 90-degree angle is not there, you see. Because remember, not all, here we have to prove it because the sketch does not necessarily have the 90-degree angle given. Remember, if I draw a circle like this and I draw a random line, if I do something like this, right, and I draw a straight line like that, do you see that these are not perpendicular to each other?
Yeah.
Yeah. So not all lines from the center will always meet a chord at an angle of 90 degrees. It's only specific ones where the what you may call, where the chord is 90 degrees with the line from the center. It's only like that if these are equal. You see, the law is almost like yin and yang. You cannot have one side without the other. So here, because they have not given us a 90-degree angle at all, we cannot now assume these are equal unless we prove it using other ways of proving. So the fortunate thing is, if you're seeing what we have gotten here, it's a 3-mark question. 3-mark questions do not need us to panic unnecessarily. See, it's a 3-mark question. If we're going to prove that P S is equal to SR, we need to just do it in like a calm manner. So it's a 3-mark question, right? Normally,
if
what
you do this, if we can also create our own line, which is MR.
Yes.
And then we say they are equal.
Yes. And then we prove that the two triangles are congruent. Just like, so it's more like proving theorem 1, you see. We're going to have to construct MR. So let's do 10.2.4. 10.2.4. We're going to have to construct MR. Once MR is constructed, we have to now show them that these two triangles are congruent. So here we're going to prove. Yes, to prove. We have to prove that triangle PMS is congruent to RMS. So the first thing we're going to state is that MR is equal to MP because they are radii, right? Yeah. And then what's the next thing we can mention?
MS is common.
Wait, MS is common. Common side.
Mhm.
And then we can then now, we have to mention a third item, remember, prove congruence. So
Mhm.
what's the third item?
So it's either side, 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 angle, side, angle, angle, angle.
Because remember,
So
angle,
here we are
angle.
working with RHS because we're trying to prove that these two are equal.
Yeah, we're trying to prove that PS is equal to SR. But then remember, we say we need a combination of three things where it's not all three angles, three angles.
Mhm.
But it can be
So
two
now we
sides.
have two sides.
Yeah. So we
can either find another side.
Well, no. We can find that. Remember, we're supposed to prove that PS is equal to SR. So we've now shown that two pairs of the sides are equal. So
Mhm.
to prove congruency, we can just find a pair of angles that are equal. Because the moment we are able to say that the angles are equal, would have then said that the triangles are congruent.
Oh.
Yeah. So here we can say
Side.
P1 is, yeah?
Side, angle, side.
Yes.
So you
So
prove
here we
okay.
say P1 is equal to SRM because they are base angles of an isosceles triangle. Do you see it? Do you see that? The green dots there. Base angles of an isosceles triangle. So here you can now say, therefore, the triangles are congruent. You see? Therefore, triangle PMS is congruent to triangle RMS. Therefore, PS is equal to SR. Well, but the reason for having to have shown the congruency there, we can say side angle side. Side angle side. There we go. You see it? Yeah. So that's how you go through this kind of question. And in things like tests and exams, you can expect questions that will be put together like this. And as you saw, Dr. Khan can help us break things down. Cool.
Okay.
Yeah.